Today's topic are support vector machines. We had 3 weeks basically of machine learning fundamentals and basics that we need to get into the field. And today is the first lesson of several where we will look into specific algorithms and get a feeling for how do they really work. And today it's about the support vector machine. We will tackle the support vector machine in 4 steps, not 3 as usual. We will first look at the basic idea, then see, okay, how can we formulate that more formally and look into mathematical definition. We will not talk much about optimization of how the SVM is trained. We will focus on how is it formulated and what can it do once it is trained. We will not look too much detail. How is it actually trained? We will not look into the optimization. Then we will talk about kernels, a very famous idea in machine learning. Sometimes you even hear the word kernel machines. You heard it a lot 15 years ago as a major area in machine learning. What today basically is deep learning, like a huge field where we most of the time just talk about neural networks. Probably you know deep learning is better than neural networks, but most of the time we regard it as synonymous. A couple of years ago we talked about kernel machines, but usually talked about support vector machines. So we will talk about the use of kernels and then look how can we extend the basic 2-class classification setting that we talk about most of the time to a multi-class setting. And the ideas here are very general, so they will also apply to any other algorithm you can. That's the plan for today. I hope that we achieve the following educational objectives. That you know the support vector method in some detail. That means you can explain how the idea evolves. We will first talk about a very simple thing called a maximal margin classifier. We will evolve the maximal margin classifier into a support vector classifier. And we will evolve the support vector classifier to a support vector machine. So we have something like a Dreisprung, a 3-step jump. And I hope you can remember this and by that explain how SVM works. And we will see 2 concrete examples of parameters with which we can basically tune the bias and variance trade-off we talked about last week. So today is the concrete example of that I spared you last week. Hopefully, by hearing all that and remembering this, you will be able to use SVMs in smaller settings and from there get a feeling for the method so you can use them in your practice as well. Lab-wise, we are still in the lab description V04 and we just go to the next section today. At the very end, I will show you a slide what basically is the task for this week. Good. Basic idea of support vector machines. Let's start very basic. When we do machine learning, we usually have these dichotomy, the two-part thing of supervised and unsupervised learning. When we have data points and we have no labels available, so if we don't know here the shape and the color, which basically show classes here, if we just have data points, what we usually do then is we do clustering. We have the data itself and we somehow try to find patterns or shapes in them. When we do supervised learning, what we usually do is we try to separate the classes. And that means we want to build a discriminative model. A model that models a line of demarcation. It does not need to be a straight line, but it could be that somehow separates the 2 different classes in the data. This is what we talked about already in week 1. Today we will look at a specific method that finds such a line that is in some sense optimal. This is what the support vector machine is all about. A little bit about notation, so we can basically follow the equations that are on the slides. The representation of a support vector machine is a hyperplane. The support vector machine algorithm constructs a hyperplane. So in 2D, this is a straight line that separates, in the case we will talk most of the time today, the 2 classes from each other. The line between the 2 classes. Constructs a hyperplane based on a representation of the data as p-dimensional vectors. So that means p-dimensional vectors, each data point has p columns or p features. Now, just so that the math keeps together later. We will talk about our features in rows and the observations in columns. That is flipped from what we talked about in the very first lecture. And in the end, you don't need really to care. But just if you wonder when we have to transpose in the equations, it's because we talk about data points that are organized as column vectors. It makes the math a little bit more tidy later on. So this will be the notation for today. What does it mean? If we would have, for example, three-dimensional data points, we have our data points, and the support vector machine constructs the p-dimensional hyperplane that somehow separates the classes from each other. The three steps I already introduced to you, we will now look into, and you will find these numbers appearing in the slides 3 times. We first talk about the very most simple case where we assume the data is linearly separable. So we assume this is the case. We can linearly separate them, and we are interested in what is the optimal hyperplane to separate the data points. And this results in the maximum margin hyperplane classifier. When we have that ready, this idea, we extend it to the case where the data is almost linearly separable. But we assume some noise on the measurements or on the data itself that makes it not completely linearly separable. And we're talking about how can we cope with some misclassifications. Can we have a mechanism to cope with some misclassified data instances and still build on the ideas what is an optimal hyperplane here. And when we have that, and we can deal with some misclassifications, by means of a hyperplane, we go to the third stage, talk about the support vector machine, talk about the name as well, why it's called the support vector machine, for the case where the data, where we have no assumptions about the separability of the data, where the data can be completely non-separable with a linear function. And we see how we can achieve that. So that's the idea of today, how we introduce it. So first idea, here's the one, the hyperplane classifier. And our assumption at the moment is data is linearly separable. So we can find a hyperplane that separates the data points. The question is which hyperplane do we find? Look at this plot of data points. 2 classes, the black and the blue. We have printed our observations. Here's a hyperplane that separates the data, but of course, we can draw lots of different hyperplanes that separate the data. Question is, which one is the best one? And support vector machine introduces the idea that the best hyperplane is the hyperplane where this area here, the area between the 2 classes, is, when this is maximized, that this is the best separating hyperplane we can find. Based on the intuitive assumption that when this area here, the no man's land or the death strip, or however you would call it, if that would be a border, if that area is maximized, we maximize the chance for generalization. Because we assume these data points in supervised learning are just samples from our original data that we want to learn about. And by chance, it could be that there are some black dots here and some blue dots here that we didn't see, just because of the sampling. And if we maximize the distance between the 2 points, then we will minimize the chance for misclassification of future instances. That's the intuitive idea why maximizing this margin, this is how it is called in the context of SVMs, is what we are striving for in SVMs. So the overarching idea is, let's fit a line, a hyperplane, through the data to separate them, and the optimization principle is make these margins as fat as possible. And this is why we call it the maximal margin hyperplane and the maximal margin hyperplane classifier. The interesting thing is, if that is our principle, and we're motivated by good generalization performance, it brings with it some very interesting properties with respect to how can we represent that thing in the end. That have some very cool effects on computational efficiency of our method. When you look here, this hyperplane and the 2 perpendicular lines that demarcate the margin, what would happen if I take away all these blue dots here, up here, and all these black dots, would the margin move? Would the hyperplane move? It's somehow it is somehow represented by only very few instances from our training set. So once we have found the optimal hyperplane with respect to that principle, it is defined by only very few instances in the data set. All the others have no influence in the end. This observation gives rise to the term support vectors. Actually, those instances from the training data set that are closest to the margin, only those define the margin. This point has no influence on the margin whatsoever. This point has no influence on the exact angle of the hyperplane whatsoever. The only points that have an influence are those that lie directly on the margin. And those points are called the support vectors. Why? Because they support the exact position of the hyperplane. So in the support vector machine, it's all about finding those support vectors that define our hyperplane. Yes?
In two-dimensional space, we always have 3 support vectors.
No, we could have more. But we will see later. It will come later when we extend the idea also to the not so very strict separable case. Then we will see how we can have more support vectors. But I would say you have at least 3. Yes?
So additional data only helps us if they are part of the support vectors, right?
Yes. Additional data only helps when they're part of the support vectors, yes. And an interesting remark follows from that. The support vector machine somehow needs to find those support vectors, and because they define the classifier, the hyperplane, they will be part of the model. The support vectors are stored within the model. This has a very interesting relation to privacy. If you train a machine learning algorithm on some data that is very confidential and you're not allowed to give the data out, and your classifier that you have chosen happens to be a support vector machine, you have to have in mind that by definition, if you give the trained model out, you give some of the training data out, because the support vectors are part of the model. So, that's a very interesting point when you think about it. By giving out the model, you are disclosing at least a small part of the training data. If this is personal data, you probably want to anonymize it before, because you don't want to give it out with the model. Good. Questions up to here? So far the idea is quite straightforward, right? And it remains straightforward, just how we optimize it is a little bit more complicated. So now that we have the basic idea, we will look a little bit into how is it formalized and how is it prepared for optimization then. You find details, basically non-overlapping details, in Chapter 9 of the Introduction to Statistical Learning and Chapter 12 in the Elements of Statistical Learning. Both books have roughly 20 pages on the method, and they are almost non-overlapping. So when you read these 20 pages, there's, I think, one paragraph of overlap, and then this is just a continuation of that. So they don't reiterate the basic principle and the intuition. They just start from where this thinks, oh, it's enough. We already know enough to understand it. And that's very interesting. Fun fact, they use exactly the same mathematical notation, but they have a different meaning for the different parameters. So when you start reading here and continue here, you have to realize that the meaning of the formula, the letters in the formulas will change. That's a little bit mean, but we will talk about it later. Good. Formal definition. What is a hyperplane? We are probably very familiar with that notation. I think in school we called it in 2 dimensions. Input is our data point x. M is the gradient of the hyperplane. B is the y-axis intercept. And with this formula, input data point times the gradient plus the y-axis intercept, we have the corresponding y value on the straight line. We are familiar with that. Here we use a slightly different definition. For the hyperplane, we use the definition of the set of all vectors x, of all points x, in all their dimensions, that satisfy the following equation. And as you see, it's a linear equation, no quadratic or whatever terms. The betas are our m and b parameters. And all the points for which this equation is 0, they lie in a straight line. If your relationship to math is a little bit like my relationship to math, you might want to take afterwards half an hour or 20 minutes or something and a pencil and a paper and just for yourself clarify that that is the same as this, but it is, I checked. So, this is a definition of all the points that lie on the hyperplane. If those points lie on the hyperplane, then the hyperplane equation for all the points on one side of the hyperplane is either greater than 0 or smaller than 0. A convention when dealing with support vector machines is a general convention in machine learning, but not for all methods, is very important to stick to it. In support vector machines, it's important to stick to it. A convention is that if we have 2 classes, we encode them, the labels, as plus and minus 1. So not as 0 and 1 for positive and negative plus, but as plus and minus 1. Why? Because the label is brought in here into the equation, and we can equivalently write label times the equation of the hyperplane with the x data point inserted. If that thing is greater than 0, we basically have a point that is not on the hyperplane but on either side. A couple of remarks. If the coefficients beta, if they have a norm of 1, so if the vector encoded by beta has a length of 1, then what the formula is actually giving us is the distance of the instance x to the line. So evaluating, including the label, the hyperplane equation for any data point x gives us the distance of the point, the straight distance of the point to the line. So this basically says how far away from the classification line, from the line of demarcation are we without the data instance. And it also tells us on which side. Good. That's the definition of the hyperplane we will use, and the definition of how do we encode the labels. The question now is, how do we find the optimal hyperplane? How do we maximize the margin? So intuitively, we can optimize it as follows. What we want to maximize is m, the margin. And by definition, the margin is the distance to the closest point on any side of the line. We want to maximize that. That's the definition of the margin. No point is closer to the classification line than the margin. We want to maximize the margin. How do we do that? By tweaking the beta parameters, because those say where in the space are classifier lines. So this maximization has some constraints that we have to fulfill. First is the betas have to have a norm of 1, so the beta vector has to have a length of 1. Why? Because we said it has to be like that on the last slide. And additionally, we enforce that every point has a distance from the line of demarcation, from the separating hyperplane, at least m for every data point.
Is the exponent 2 with the equation is the inside of the sum or outside of the sum?
That's inside. it have to be outside?
For me, it would be more looking to be it out if it have to be outside. But I'm not sure. That's my question.
It's inside, and I think it's correct, but I will check. Any opinion on that? Can we resolve that point here? Yes?
I mean, when it's the length of the vector, then it's inside.
That would be the case.
The negative value, no? Because they can, it's inside for the negative value, because if you sum up and it's not,
Yes, exactly.
it will be also.
So for the definition of the length of the vector, what do we usually have there? We have a vector x1 with 3 components, say, and we want to have the length of that vector. Then usually what we do is we sum the individual things up. And if you and sometimes take the square root, which is actually yeah. So it has to be inside. That is what we would intuitively do in order to find our hyperplane. We want to maximize the margin. For that, we tweak parameters subject to 2 constraints. So we have a constraint optimization problem. But due to several reasons, it's not a good idea to directly solve that constraint optimization problem, but to reformulate it a little bit in order to be able to use a specific optimization method. The optimization method used here are the so-called Lagrange multipliers. And to use Lagrange multipliers, we technically have to reformulate the problem here that way. What we will not do today is to dive into how do Lagrange multipliers work and what exactly will be done technically, like algorithmically, to find the betas in the end. There's one thing that makes it necessary that we have a look at the equation anyway. This is the equation that is optimized in order to train the support vector machine, in order to find the best optimal classification line, hyperplane. So in the training procedure, of course, the training data somehow goes into it, right? When you want to train a classifier, data has to come in. The data points are the axis. Here we have our axis. The axis go into this equation exactly and only at that place. If you look closely, what you see is that the x vectors, 2 different x vectors, go into the equation only in form of an inner product, or so-called scalar product. Right? We have a vector here, we take the transpose of it, and we multiply it with a vector of the same shape. So we have a column vector transposed by a column vector. Result is a scalar. So our features, our data points, don't enter in their complete dimensionality into the equation. They only enter as inner products. That is a very, very interesting property of support vector machines, and it allows some very interesting tricks we will talk about in the second part of the lecture today. And we will come back to that equation. What we have seen so far is that the best classification hyperplane we can construct is the one with the biggest margin. And that in order to do so, we can use Lagrange multipliers and apply an optimization strategy and find our beta parameters that fully define the hyperplane. So we can find this using that method for linearly separable data. Now the problem is almost all data we have in practice is non-linearly separable, which in the first place means it's not linearly separable by linear function. There will be data on the wrong side of the hyperplane. Sometimes it might be, as in this case, that we find a linearly separating hyperplane that can, in fact, without any error, discern our training data. But you see here, the margin becomes very marginal, so to say. What we would much more likely want is to still have a big margin and allow for some misclassifications during training. So in the case where we assume that already our training data, probably due to noise, to inconsistencies in how we collected the data, will not be completely linearly separable, we still want to find a hyperplane classifier with a flat margin. And we somehow will then have to deal with some points that violate the margin condition, rather than finding a hyperplane that actually separates the data perfectly but has no margin at all. Why? Because we think that this thing will probably overfit to noise in the data, while this thing might in the end be much better to generalize. So we still hold to the idea that a bigger margin has advantages when it comes to unseen data and generalization, and we don't want to overfit and sacrifice our margin just to fit all the points in the training set, because we assume that the data is anyway not linearly separable. Okay, so that is a setting. How do we do that? How can we optimize still for a big margin when by definition of the margin no point is allowed to be within the margin? That's a contradiction, right? We want to have a flat margin, but we will have points in the margin. What's the margin then? The solution, the idea behind the support vector classifier is to come up with a penalty factor called C that penalizes misclassifications up to a certain amount and still guarantees large margins. So we will have misclassifications and we will have a penalty on them, and if we make the penalty large, this will probably result in having no misclassifications and a trained classifier like that. And if we bring the penalty factor down, we will allow some points violating the margin condition and have a fatter margin anyway. And with this C that we can increase or decrease, we can somehow control how fitting the model should be to the actual training data, and vice versa, how good it should generalize in the future. Let's have a look into that in a more formal way. We still want to maximize our margin, and we still do that by finding the optimal beta parameter vector. We still have the constraints that the size of the vector, beta vector should be 1. We still have the constraints that all our data points should have a distance of at least m to the classification line, but we add some slack variables here. These C variables are indexed by I, meaning we have a C variable for every instance in our data set. It's the same index we have here for the data points x. So we have a slack variable C for every instance of the data points. And you can think of this C being a budget that you have for misclassifications. And the overall budget, this is the third constraint here, the overall budget is given by a parameter C tilde. You see here, I call it C tilde. Do you call it tilde? Tilde? C whatever, something above it. This thing is not the same as the C parameter we saw on the last slide. In fact, they are anti-proportionally related. And that's exactly the mismatch you have between the two statistical learning books. In one book, the thing is called C, and the other one is called C something else, and they have opposite meaning. So if you talk about a big C parameter, that means a small C tilde parameter, and vice versa. Actually, to understand how this budget for misclassifications works, it's much better to talk about the C tilde instead of the C from the last slide, even if you have to adjust the C when you implement SVMs. So, what is C tilde? C tilde is our overall budget in terms of distance of misclassifications. Imagine the following. When you have a classification line, and then we have the margin, and you have a point here on the wrong side of the margin. Then it takes this much budget for misclassification from the overall budget C tilde. This amount here. This is its, how do you write this thing? This is its personal C slack variable, and it takes the amount of how far is it from the classification line on the wrong side. If you have another data point from the red, so this is red territory. If you have another data point here, it would take this much of our budget for misclassification. And this is maybe too much. So we will rather move the classification line a little up. So this is the idea. Every data point comes with a slack variable that we can give or allot some portion of our overall budget for how far on the wrong side of the classification line can a data point be. If we make that budget large, basically the classifier can ignore all the data. And it can position the hyperplane however it wants in the room, in the space. If we make it very small, we are back to the case of the maximal margin classifier. We don't allow for any misclassification. How does that look like? Varying at C or C tilde parameter. Let's have a look at that. What we see here is a visualization for some data points. We have two classes in 2D, the green and the red data points, and we want to find the maximal margin hyperplane classifier, or coordinate classifier even. And we are varying now the C parameter, so the penalty from this classification, the inverse, so to say, of the budget from this classification. And we will look at how does the classification line look like. Where is it? The colors are as follows. Support vectors have that blue circle around it. Green and red are the classes and the instances from our training set. Black is the margin. Red and green is the area where something is classified as red or green. And the classification hyperplane is actually white. And because we currently have a very, very low penalty for misclassification, corresponding to a very, very high budget for misclassification, our classifier actually learned a hyperplane that doesn't care for the data. It's somewhere up here. What we will now see is when we increase the C, the penalty for misclassification, that this line will come at a more reasonable place. So let's see how it happens. At the moment, we have a low C, no penalty for misclassification. Sorry. Is that true? The low C, that means a low penalty for misclassification, that means we have a gigantic margin. Yes, exactly. That's true. So, let's increase the C. You saw what happened? We came from 0.05, we doubled it basically. And you see the white line the hyperplane comes down nearer to the data. Now, actually, for the first time, you see that the white thing is a classification line. And we see, okay, green is on that side, red is on that side, the margin is still really, really high. Almost all training data points are support vectors. Why? Because they are either on or in the margin. That's the answer to the question from earlier. Can we have in 2D more than 3 support vectors? We can in the case of mislabeled data points, because not only the points on the margin, but also all the points on the wrong side of the margin or in the margin are support vectors. When we still increase the penalty for misclassification, the margin becomes smaller. And also the orientation of the line changes in order to regard the data points better and still keep a big margin. This point is a support vector because it's on the wrong side of the classification line. So all the points on or within the margin plus the ones on the wrong side are support vectors. So now we're already at a C of 100. We have now increased it tenfold. And that now somehow looks like a reasonable classifier. Let's go through it quickly again, and I would ask you to pay attention to the actual value of the C. So if it is too small, the thing learns nothing really from the data, it just ignores it. It is increased here by, for example, doubling it, increasing it 4 times, doubling it, times 10 or something, even more, times 4, doubling it, times 10. This parameter C is a hyperparameter that controls bias variance trade-off, as we discussed it last week. As you see here, it's very difficult to set it like blindfoldedly without looking at the data. This is a very good example why I told you in the beginning, doing machine learning means to work empirically. It means to actually look at your data, do experiments in a systematic way, and find out what actually makes sense. There's only little theoretical things you could do to say upfront without trying something, oh, I should use a C of 768.5. It's actually much more reasonable to think about a scheme starting from a lower bound up to an upper bound with a certain increment, trying several values and find out which hyperparameter works best here. And also what is reasonable. This now looks quite reasonable. Yes, you don't overfit, you still have data points on the wrong side. So it doesn't seem to overfit completely. The margin is reasonably big. Sounds like a good choice. And the choice between 1000 and 100 is actually not a big difference here. But between 100 and 51, also not a big difference, but this is already a big difference. This line looks much better than this one, just for visual appearance. So this should give you some intuition on how does doing machine learning look like. You have to fiddle around with these hyperparameters, as long as you're not using an automatic machine learning system that can also train these hyperparameters. Okay, questions up to here? Yes?
So that means with a support vector machine we could also compute the expected error rate, because we know how many data points we misclassified in our training.
I would be careful with that. Of course, basically knowing how many data points are misclassified and how far they are from the what do we call it, the classifier basically, yes, how far they are from the classification line, it tells you something. But it's still, this would be some version of calculating the error on the training set that the algorithm has seen during training. And as we learned last week, this is hopefully, hopelessly optimistic. You cannot predict the true error from these measurements. It tells you how consistent is your data set, because you see, oh, I have misclassifications or I haven't. So it tells you something, but it doesn't tell you what can you expect on unseen data. It doesn't tell you. Okay. I would say we make a break for the next 5 minutes and then continue.